So, nu star, okay, what happened to nu star? So, this is a picture somewhere down the line. Nu star is bit around 0.5 for our for all B's, around 0.5. This is a range. I am going to show you one slide, but the question is, yeah, this is the nu star. Okay, so nu star is for this x axis is B and y axis is nu star and Kolmogorov constant too, but we will discuss that Kolmogorov constant computation later. So, nu star is ranging from around 0.5, it decreases to around 0.4. It is function of B, but it is around 0.4, 0.5, and interestingly this is also the number which you obtain in Navier-Stokes equation. So, cell model is giving us a very good handle on computing nu star. This from theory, okay, the formula which I just wrote, I just substituted there and take square root, I will get nu star. But how do I verify using numerical simulation? The solid line is our theory, and the numerical simulation we did. I am going to show you how I can get these numbers for different B, and they are quite close to the theoretical work. So, how do I do it? So, these were how to compute nu n from simulation. So, remember this is an assumption, but it is a good assumption. So, what is in physics we make models, there is nothing called perfect theory in physics. New theory is proven in physics. Mathematics we prove theorems, but in physics we never prove theorems. We say that if I do some computation and that matches with the experiment or numerical simulation, then my theory is good. But tomorrow's experiment may go against my theory by some regime, it may not work, then my theory has to be remodified or maybe abandoned and new theory should be created. So, it turns out this model is good, it works to good approximation, okay, for small times, small t minus t prime. Okay. So, let us see whether this thing works in simulation. What is C bar? It is u n at time t, u n star t prime. Okay, t and t prime are shifted. Okay, this is this quantity. So, I can compute this in numerical simulations. I get a time series of u n, I get time series of, and I just shift it and compute this this correlation function. Okay. So, in fact, I divide this by u n t squared. So, this will give me what? This exponential part. So, I take this unequal time correlation, divide by equal time correlation, I get a time series and I compare it with exponential. Okay. So, this is what we do in simulation, and this was done by Sadab in our lab. So, x axis is we put nu n k n squared tau, and y axis is that normalized correlation, this one, C bar by C, and for this is non dimensional quantity. So, for this band, this exponential some constant times k n to the power 2/3 tau is a good fit. Okay. In simulation this is what we get. I am not going to exact like things fit on the line. This macroscopic phenomena we do not get like on dot. I mean this is not GR verification. Okay. This is what we get pretty approximate curves. Okay. Now, but interestingly this is going as k n to the 2/3. Nu n k n squared is k n 2/3, right, because nu n is k minus 4/3 and this q2. So, great, I mean this function of k n is working. Now, coefficient is 0.57. Now, what should I compare this 0.7 with? 0.57 with? This 0.57, so you can look at it here, okay. Nu n k n squared, this k n squared is k n 2/3 is here, and this whole object must be same as 0.57, right. I compare. So, nu star square root k Kolmogorov epsilon 1/3 is 0.57, 0.57. Okay. Now, epsilon on your simulation was 2. Okay. K Kolmogorov, of course, I need it because I can't. So, we took k Kolmogorov from theory, I think it is around 1.7 square root, then that will give me nu star, and that is how we compute nu star from simulation. And that nu star is matching reasonably well, of course not on the line, but reasonably well with the simulation, with the analytical prediction. Simulation results are close to the analytical prediction, and that is how we compute nu star. Okay. So, this is what we get here, and this is for different B we can compute it. We did this for different B's. Shell model is pretty cheap, so we can do it for many runs. Now, these are non-equilibrium solution, but we also can work equilibrium solution for shell model. So, remember RHS was un plus 1 un plus 2, right. So, RHS was nu n plus non un plus 1, sorry un plus 1 greater, un plus 2 greater, there is a star in one of them. Okay. So, for equilibrium solution un plus 1 un plus 2 are totally random, white noise. So, this is 0. So, there is no correction to nu bar, because right hand side was 0, where right hand side is 0 for this. So, for equilibrium solution there is no correction to nu bar. So, nu bar is same at all scales or all UNs for Euler equation, and that is what we get here. This is 0. So, we basically get the right hand side is 0. So, there is no renormalization for Euler equation. Okay. So, equilibrium solutions are somewhat trivial that way, and no correction. So, summary for RG is in turbulent scenario nu n is function of k, which is k n minus 4/3, and nu star is roughly 0.5. Kolmogorov solution works here. Well, I did not say that Kolmogorov solution is a unique solution, but I said it is one of the solutions. So, this is called self consistent. Well, let me guess it works or not, and look, it works, that is what we say. This is a self consistent theory, and equilibrium case basically is no renormalization. Okay. So, I think I did a lot of things, but I hope it is clear most of it. Any questions? No. This idea is not to find a solution of UN. Idea is to find correction to nu bar.
Because this is function of time in fact, right?
So we are, well, okay, good question. So, I am making an assumption that I force at large scale. I should have mentioned it, but I did not. I force at large scale, this is a cascade, but in the inertial range force is not playing any role. So, F is not appearing in the inertial range equation for RG equation, and we are looking for the effect of the coarse grain modes un plus 1 un plus 2 on the viscosity under for steady solution of un. So, let me go back to the idea is not to solve this equation, that is not the idea. Idea is look for correction to. So, we are looking for, okay, so I should go to previous slide. Yeah, my idea is to look for the how the nu bar is getting increased or is increasing because of this term which is averaged out. So, look, in this room I have full Navier-Stokes equation, but I do not want to look at small scale of the flow of the room like large UD simulation. When I filter them out, then what is the enhanced viscosity at a bigger scale, at LES scales. So, our modes were all the way, right. Let us say, in fact, when I was doing it I did not go all the way, I had up to kn plus 2, kn plus 1 kn, I had up to kn plus 2, but I will say, well, what is if I go up to only kn, I do not keep these two modes, then what is my viscosity at kn? That is what I am looking at. So, my objective is not to solve the shell model, but my objective is to look at the effective viscosity.
How do you calculate effective viscosity from the direct numerical simulation?
Oh, so that was what I said. I compute the correlation un plus 1 un t un t prime. Okay, so let's I will go to that. I will go to that equation. Yeah, so I compute this object, which is un t prime. So this is your time series, no? So I can do there is a complex conjugate in one of them. Then I divide by un mod un square average. So this will give me this exponential part.
Solution does not look like this exponential part.
Why? This is the real solution we got.
If it will be exponential, then it should be linear function.
This is a semi-log y, and it is linear in that part. It is not for all scales. It is for,
This is my point. Why it is not?
oh no. So this is the RG equation, RG u nu n is not does not work for all times. It later for bigger times is a decorrelation. This works the Markovian approximation. So this will work only when for this is order less than equal order 1. This is a what we see. My formula, this formula is not going to work for all times,
The given n,
right?
the curve show us the real C bar, right?
This one, this is Rn, this is Rn. Now, this is exactly this.
So but you hit it by the exponential.
So this is exponential constant. This is k in 2/3. This guy is function of k in 2/3. You mean all the way like that?
Yes.
No, it doesn't. Well, we have worked. Infinite is not supposed to work. No, by the way, it is. This is
I mean,
no.
I will get
By the way, this is not expected to work. In fact, it is wrong to extend it to large T. This is the condition. This condition less than equal to 1. Okay, 1 is somewhere here. Okay, so it doesn't go up to 1. Okay, it doesn't go up to 1. Now DNS okay, maybe something different, but this is trial and error, and that's what we get. In fact, this is somewhere here 0.7 or something, 0.7. That's only up to that. But this kn, whether this kn, these are all inertial range gains. These guys are inertial range. Our kn is inertial range, but the time, but according to me, nobody has computed this first shell model. What I showed you, this one. So this shell model, this is a correlation. By the way, if you go for long time, then this is anti-correlated, or rather zero correlation. This guy, this correlation will become 0 for large t minus t prime. So this is expected to work only for this band, not for all t.
This memory time.
Yes, Markovian approximation. That's right. Yeah. Okay. Okay. Anything else? Is it clear or not clear? Okay. So I think are you guys all tired, or we want to do the next one? How many for next one? I am a bit tired, but I can go on for half an hour. So next is flux. How to compute Kolmogorov constant? That's the next one, which has less slides, but okay, maybe we should do next time, right? I think it's saturation, reaching saturation. How many for today? Okay, so I think we'll go to the next one. But so let's record for a little bit. One more few things which I missed out. I should. Okay, so few important point we should remember. So this is the first real RG calculation for non-equilibrium system. So you might have noticed some differences. I mean, if you pay attention, and with some, well, you may not have noticed. So you can compare with Wilson 5/4 RG with shell model RG. So few things which are obvious, the d by dt, there was no time here at all, d by dt was 0. Here d by dt is there, is a dynamic, but of course, we are looking at steady state. So, d by dt is not playing a big role, but it is a steady state what we look at. Second important point is the Green's function and correlation functions g of k and c of k. There was no time in it. Remember, there was no time in it. It was time independent. It was equilibrium system. But the equilibrium system, time is frozen. Huh? Time does not change. If you are in equilibrium, then time does not move for you. There is no arrow of time for equilibrium systems. Okay. So, g of k, c of k's are independent of time. Here, g of k and c of k are dependent on t minus t prime, and they are different functions. One of them was theta t minus t prime exponential, other one was ck. So, they are different functions, they are not the same functions, and they are function of time. Here the flux was 0, equilibrium system flux is 0, not only in 5-4 theory, but also for Euler equation. But non-equilibrium system pi k is not 0, radial balance is broken. Okay. So, there are, so I gave only one scheme, self consistent theory. This is one of the simplest demonstration of non-equilibrium renormalization group. There are more complex ones. So, I will mention them later. So, there are like Yacob-Herzog is one of the most famous Yacob-Herzog for Yacob-Herzog 1986. Then there is a Martin Sigia, it is called MRH, Martin Rose Sigia. I think this is 73 or something. FNS, Foster, Nelson, Stefan, 76. So, there are different schemes to do RG. The RG is, so we can do functional renormalization using partition function. Similar things is done here. I use basically differential equation. Okay. So, I do not think we have time to get into details of it, but I will try to mention gist of it for 2 minutes for each of them a little bit later. Okay. So, so for point to note is that this non-equilibrium and equilibrium RGs are different. Okay. But of course, there are common theme that we do coarse graining and effect of coarse graining on different scales. That is a common theme, but the tools and assumptions are different. Okay. So, let us stop here and I will do the flux part in the next class. Okay. Thank you.